we start with trig with right angle triangles, but of course angles don't stop at 90 degrees. I mean, they keep going. So how do we handle angles that are not in a right angle triangle? They are of any magnitude. So to do it, we look at our good old unit circle here. Now 0 degrees, we always seem to define things to the positive x-axis. You might remember in coordinate geometry, when you find the slope of a line, it's the angle of inclination to the positive x-axis. Any of you know anything about complex numbers, you'll know that the argument is defined to the positive x-axis. So things like that. So we start there at 0 degrees and we go around anti-clockwise and obviously come back at 360 degrees. Our quadrants also go in that order. So first quadrant's where everything's positive. Third quadrant would be where everything's negative, and so on. The little butterfly, I call it, what it basically is, I'm drawing a right angle triangle in each of the quadrants. Okay. Now, we want the x value and the y value on the circle, so that's why I've drawn the triangles the way they are, because that will tell me the height of the triangle and the length of the triangle down the bottom. And this allows us to handle angles of any magnitude, because we bring it back to an acute angle. And theta I've marked in would be the acute angle, and of course in my diagram all those angles are equal because we've got vertically opposite angles, we've got symmetry, would be easy enough to prove they're all theta. So in the first quadrant everything's fine because we're between 0 and 90 degrees. Once we get into our second quadrant, the quadrant which I call 180 minus theta, theta being the acute angle that I want to bring it back to, we have a look. Now if you have a look at the triangle in the second quadrant, the sine ratio we said was opposite over hypotenuse. Now the opposite would be the y value of that point, and the y value is positive. And the hypotenuse, well the hypotenuse is simply a distance, and distances are always positive. So we've got positive over positive, so the sine ratio is positive in the second quadrant. If we look at cosine adjacent, well the x value would actually be negative in the second quadrant. So we get negative over positive, so cosine is negative. And similarly, with tan, the y value, or the opposite side, is positive, the adjacent side is negative, so we get negative. So that's how we get the sign of our different ratios. In quadrant 3, turns out that tan is the positive one, the other two are negative. And in quadrant 4, it's cosine turns out to be the positive one, and the others are negative. But again, notice how I've labelled them. Quadrant 2 I've called the 180 minus theta. Quadrant 3, 180 plus theta. Quadrant 4, 360 minus theta. The reason I've called them that, have a look at the diagram. We always start at 0, we go around anti-clockwise. So in the second quadrant, I've stopped theta short of 180, so 180 minus theta. Whereas if I keep going to the third quadrant, it's 180 plus theta. Third quadrant, I'll keep going around and I've stopped short theta of 360. 360 minus theta. Because what we want to do is get everything back to 0 and 90, between 0 and 90. So if I had to find 260 degrees, I'd say, well hang on, 260, that's in the third quadrant. So I know it'll be negative. It would be the same as the acute angle. Well, the third quadrant is 180 plus the acute angle. So it must have been 180 plus 80 to get to 260. So the acute angle there would be 80 degrees. So it would turn out to be the same as if I wanted to work out the sine of 80 degrees, and it would be negative 0.9848. You think, well, that's a bit of an odd way of doing it. Why didn't you just press the buttons on your calculator and you would have got an answer? Well, of course, this technique comes from before we had calculators. And they used to use table of values. And they didn't have table of values for every single possible angles. They just had a table of values for the acute angles. And so you had to do this. You had to build it back to the acute angle, and then you look up your table of values for the acute angle, and bang, that was the answer. The idea is still important though when it comes to solving equations and things like that. So tan 220, third quadrant, the acute angle would be 40. You'll find that tan 220 would give you the same answer as tan 40. Secant, no, you don't have a secant button on your calculator, of course. So we have to play with our reciprocal button. It'll be the same as the negative secant of 75, but how would I do it on the calculator? I'd find the cosine of 75 and then use my reciprocal button and turn it upside down. You don't have to stop at 360. That's the thing about a circle. It keeps going round and round and round and round and round. So basically you keep taking off 360 until you get to a number in between 0 and 360 and then get it back to its acute angle. In this case I only have to subtract the 360. I get 70. 70 is acute, so that would be 0.3420. There's no reason why we have to go anti-clockwise. We could turn clockwise, but that would be a negative angle rather than a positive angle if we go clockwise. So the tan of negative 67, so I'm going clockwise 67 degrees. I'm in the fourth quadrant. I just find it a little bit easier, say, oh no, let's just add 360 to it. 293, okay, that's in the fourth quadrant, and amazingly it turns out to be negative tan 67. By the way, what does that tell me about the tan function? It's an odd function. See, tan of negative x is equal to the negative of tan x, and if you think of your tan curve, sure enough, it has rotational symmetry around the origin. That's just an aside. But anyway, so we get negative 2.3559. Okay, so I've got to find the coordinates of P. I know that angle's 30, radius of the circle's 5. Well, it's just a matter of drawing up a triangle. X over 5 cos 30, 5 times cos 30. Cos 30, of course, is one of our exact ratios. Root 3 on 2, 5 root 3 on 2. The y coordinates ends up being 5 on 2. So to answer the question, I don't leave it like that. The question said, what are the coordinates? So I write my answer as coordinates, 5 root 3 on 2 and 5 on 2. Now what about the boundary values? We talked about in between 0 and 90, in between 90 and 180. What happens on the boundary? So to do this, I use a fictitious triangle. It's a triangle that can't possibly exist. You see, it's a right-angled triangle where that angle there is 0. So by an angle sum of a triangle, the other one must be 90. Okay. Now, the base of this triangle is 1. But if you think about it, if that angle is 0, I'm really talking about a straight line. So therefore, the hypotenuse must also be 1. And then by Pythagoras, I can work out that the height is 0. Okay, so there's my triangle. So now I can work out, I'll just read off. Oh, well, yes, the sine of 0, opposite over hypotenuse, oh, that's 0. Adjacent 1 and tan would be 0 as well. 90 degrees, read off that one. Now, it's not until we get to tan we get a problem. We get 1 over 0, which is, of course, undefined. You can't find the tan of 90 degrees. That's why you have a vertical asymptote in the graph. I get to 180 degrees and I say, which quadrant am I in? Well, I'm on the boundary of the second and the third quadrant. So which one do you want it to be in? It doesn't really matter, because in the second quadrant sine is positive. In the third quadrant sine is negative. So if it's just changed from positive to negative, there's only one thing it could be, and that's 0. Cos of 180, second quadrant it's negative. Third quadrant it's negative, so I know it's going to be negative. Negative what? Well, if it's in the second quadrant, I'd say it's 180 minus the acute angle. So 180 would be the same as 180 minus 0. And the cos of 0 is 1, so it's negative 1. And tan 180, I could do a similar thing. Hang on, second quadrant's negative, third quadrant's positive, changes from negative to positive, must be 0. And then we get to 270 and we can do a similar thing. And 360, of course, we're back at 0. Now the reality is with the boundary values, when you look at them, they're all 0, 1 or undefined. So your calculator is probably the simplest way of doing it. What's the cosine of 0? Oh, thank you. So in reality, that's probably how you would do it. So let's now have a look at the basic graphs. And the key is the boundary values. So if I do sine, I know the sine curve goes between -1 and 1. Okay, that's the range of a sine function. I'm going to mark off each of the boundary values whilst I'm only labelling it at 180, I'll put a mark there at 90 degrees, I'll have some negative ones as well. And I know the sine of 0 is 0, so I'll plot that in. We know the sine of 90 is 1. We said the sine of 180 was 0, and then that pattern continues up and down, up and down, up and down, and we get a lovely and by the way, we're not playing dot to dot here. So it's not a zigzag, it's a lovely curve. So y equals sine x. Domain, or real x, there's no breaks in the sine curve. The range in between -1 and 1. The period is 360 degrees. Period, what's that? The period is how long does it take until the curve repeats. But not just repeats and travelling in the same direction. Because if I was to have a look at 0, 0, I'd say, well, it only takes 180 degrees till I'm back at 0. But that's not the period. Because at 0, 0, I'm travelling up, but 180 degrees, I'm travelling down. It's not until I get to 360 that I'm travelling back up again. So it has to be the same value, but also travelling, if you like, in the same direction. Other important things. It is, of course, we can see it, an odd function. It has rotational symmetry. That comes in handy because that now means the sine of negative x is always equal to the negative of sine x. So that could be a handy relationship to know. Alright, let's look at cosine. So again, it goes between -1 and 1, plotted in the boundary values. Now my cosine curve begins at the amplitude. Right? Cosine of 0 was 1. So I'll plot that in. Cosine of 90 was 0, and once again that pattern continues down, up. And once again we draw a nice curve in, and there's cosine x, and the first thing we notice is they're very similar graphs. But that's to be expected, because remember co stood for complementary. The two angles always add up to 90. So I could have, instead of saying this is the cosine of x, I could have said this is the sine of 90 minus x. And what we're seeing from our shifting, what does that mean? Well, if it's 90 minus x, that means, well, the minus x means I've flipped it vertically, and then I've got a shift of 90 degrees. And if you look at those two curves, you'll see that, yes, indeed, there's a shift of 90 degrees happening there, and it's been flipped as well when you do that. What that means is the domain, the range, the period should all stay the same, because it is the same graph, just been shifted a little bit. So domain or real x, range -1 to 1, period is 360, but if we look at this graph, it's not an odd function. It's actually an even function. It's got line symmetry. I could fold that graph on top of itself. So that means the cosine of negative x will always equal the cosine of x. Again, could be a handy relationship to know. Let's complete the sets. Let's draw tan. Phew, got the axes drawn up already. Save a bit of time there. Now what happened with our tan? We started off tan 0 was 0. Tan 90 was undefined. So I'll draw in an asymptote. That pattern continues. So we go 0, asymptote, 0, asymptote, 0, asymptote, 0, asymptote, 0, asymptote, and so on. We know curves always bend towards the asymptote. I must go through the x-intercept. So what are my choices? I could have an inflecting shape, and it could go one of two ways. I might have a U shape, could be up or down. Well, that's where the quadrants come in handy. We know that in quadrant 1 the curve is positive. We know in quadrant 4 it's negative. So therefore it must do that sort of shape. Now a word of warning when you're drawing a tan curve. Yes, there is what we call a point of inflection at the origin. It is not like the cubic. The cubic's got what we call a horizontal point of inflection. This one is not a horizontal point of inflection. It comes through at 45 degrees. If I was to draw a tangent at the origin, it would be at 45 degrees. Whereas with the cubic, if I was to draw a tangent, it would be horizontal. Okay? So be careful with that when you draw tan curves. Right? They come through at 45 degrees, and that pattern is just repeated between all of the asymptotes. That makes writing domain a lot of fun. Yes, a very large box too, so I can do it. That's how I've described it. So it's all real x. We've got every possible value of x. Hang on a sec. It can't be 90. And every 180 degrees before and after it also is an asymptote. So I've just said, well, plus 180k, where k is an integer. So any multiple of 180 before or after, we should also have an asymptote. The range is a lot easier. There's no breaks vertically. So all real y. The period is only 180 degrees for the tan curve. And, we mentioned this before, it's got the rotational symmetry. So we know it is an odd function, which means the tan of negative x is equal to the negative tan of x. Now I'm just going to draw one of the reciprocal graphs. Remember, we've learned how to draw reciprocal graphs. So if I now want to draw cosec x, it's the reciprocal of sine. So let's put the sine in there. There's my construction graph. I'm going to turn this upside down. Now what did we say about reciprocal graphs? We said everywhere there was an x-intercept was going to become an asymptote. So I now have all these asymptotes in here. The other key feature was the value of 1. Remember, whenever it was above 1, it went below. Whenever it was below 1, it went above. Well, we know those peaks are all at 1. So they will stay the same. We know all those peaks will stay the same. However, if I just look between 0 and 180, the red curve is totally below the dot. So when I turn it upside down, it'll go totally above. And so on and so on. And so we get a whole series of U-shapes that are bending towards the asymptote. So that would be the cosecant of x. Domain, I'd have to do a similar thing like I did for the tan curve, but the domain would be simply, well, x can't equal 0. I'm not going to write 0 down, but I'd just write 180k, where k is an integer. Range would be y is less than or equal to negative 1, y is greater than or equal to 1. Its period is also 360 degrees, and it is an odd function, isn't it? You could have rotational symmetry there. All right. Whew, that was a lot of talking today. So 4D.